There is a strange rule-breaking behavior happening in almost every freezer, drink, and frozen lake. Yet, most of us never stop to question it. A solid that should sink somehow rises instead, quietly defying what we expect matter to do based on everyday experience. This small anomaly has shaped ecosystems, climates, and even the long-term survival of life in cold environments, often without us realizing it. So why does ice float instead of sinking? That simple question leads into the unusual physics of water, the hidden structure of its molecules, and the reason this familiar behavior matters far more than it seems. Let's dive into it, right here, on History of Simple Things. The reason ice floats begins with density, a fundamental concept in physics and chemistry. Density measures how much mass is packed into a specific volume, which determines whether a substance sinks or floats when placed in a liquid. Objects denser than a liquid sink, while less dense objects float. Liquid water near room temperature has a density of about 1 gram per cubic centimeter, which is why it is commonly used as a reference point in scientific measurements. Ice, however, has a lower density of roughly 0.92 grams per cubic centimeter. That difference may appear small, but it is enough to keep ice at the surface. This explains what happens, but not why water behaves this way. To answer that, we must move beyond visible behavior and examine the microscopic structure of water itself, where the real explanation begins to emerge. A single water molecule consists of one oxygen atom bonded to 2 hydrogen atoms in a bent shape rather than a straight line. This geometry creates an uneven electrical charge across the molecule. Oxygen pulls electrons more strongly, giving it a slight negative charge, while the hydrogen atoms carry slight positive charges. This imbalance allows water molecules to attract one another through hydrogen bonds. These bonds are weaker than the covalent bonds within the molecule, but they are strong enough to shape water's behavior. In liquid water, hydrogen bonds constantly form and break, creating a shifting network that keeps molecules close together while still allowing them to move freely, flow, and respond to changes in temperature and pressure. As water cools, its molecules lose energy and move more slowly, causing them to draw closer together, which is typical for most liquids. Water follows this pattern until it reaches about 4 degrees Celsius, where it becomes as dense as it will ever be. Below this temperature, water begins behaving differently. Hydrogen bonds start organizing molecules into more stable arrangements that require additional space. Instead of packing tightly, the molecules form structured patterns that hold them slightly apart. This causes water to expand as it continues cooling, reducing its density. This unusual shift is critical because it explains why colder liquid water can actually become less dense as it approaches the freezing point. When water freezes, the structured arrangement driven by hydrogen bonding becomes locked in place. Ice forms a rigid hexagonal lattice in which each molecule is bonded to several others in a fixed pattern. This lattice is stable but inefficient in terms of space, leaving empty gaps between molecules. These gaps increase the total volume of the solid compared to liquid water. Since the mass remains unchanged, while the volume increases, the density drops. This is why ice floats. This expansion during freezing also explains why water can crack rocks, split pavement, and burst pipes. Unlike most substances, water becomes more expansive and physically disruptive as it transitions from liquid to solid. Floating ice plays a vital role in preserving life in cold environments. When lakes, rivers, and ponds freeze, ice forms on the surface first, creating a barrier between the water below and the cold air above. This surface ice acts as insulation, slowing heat loss from the liquid beneath it. As a result, water below the ice can remain liquid even during extended periods of freezing temperatures. Fish, aquatic plants, insects, and microorganisms depend on this stable environment to survive winter. If ice were denser than water and sank, bodies of water would freeze from the bottom upward, often becoming completely solid and making many freshwater ecosystems unsustainable. Ice floating on water also influences Earth on a global scale. Ice and snow reflect a significant portion of incoming sunlight back into space, a process known as the albedo effect. This reflection helps regulate Earth's temperature by limiting heat absorption. In the oceans, floating sea ice affects salinity as it forms and melts, influencing ocean currents that distribute heat around the planet. These currents shape regional climates and weather patterns. Over long time scales, changes in floating ice coverage can amplify warming or cooling trends, demonstrating how a molecular property of water plays a role in climate stability and planetary habitability. Ice floats because water molecules form an open, hydrogen-bonded structure when they freeze, making ice less dense than liquid water. This rare behavior sets water apart from most substances and leads to consequences far greater than it first appears. By floating, ice protects aquatic life during winter, slows heat loss from lakes and oceans, and helps regulate Earth's climate through reflection and insulation. What seems like a simple curiosity turns out to be a quiet, stabilizing force in nature. Every floating ice cube reflects a molecular rule that supports ecosystems, shapes environments, and helps keep Earth stable and livable. Thank you for watching. If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution. Thank you for joining us on this journey through the history of simple things. Don't forget to like, subscribe, and stay tuned for more stories woven through the smallest details.